Imagine standing in complete darkness. Not the darkness of a room with the curtains drawn, not the darkness of a forest at midnight, but a darkness so absolute, so total, that light itself has never touched it. A darkness older than stars. A darkness that makes up most of everything that has ever existed. And somewhere in that darkness, forces are at work that no human being has ever seen, measured, or fully understood. Forces that are pulling the universe apart at speeds that should be impossible. Forces that bend reality itself. Forces that, according to our best science, should not exist at all. And yet they do. Welcome to the edge of human knowledge. Welcome to the place where the equations break down, where the telescopes go blind, where the most brilliant minds on Earth stare into the void and whisper, quietly, to themselves, "We don't know. We simply do not know." You are about to take a journey through the most unexplained phenomena in the observable universe. Not science fiction, not mythology, not the conspiracy theories of people who distrust institutions. These are real phenomena, documented, measured, confirmed by multiple independent observations using the most sophisticated instruments humanity has ever built. And they are completely, utterly, bewilderingly unexplained. Before we go any further, ask yourself this: how comfortable are you with not knowing? Because the universe, as it turns out, is extraordinarily comfortable with keeping secrets. It has been keeping them for nearly 14 billion years. And the more we look, the more we realize that the things we don't understand vastly outnumber the things we do. In fact, by the best current estimates from cosmologists at institutions like NASA, the European Space Agency, and leading universities around the world, approximately 95% of the universe is made of stuff we cannot see, cannot touch, and cannot explain. 95%. Think about that. Everything you have ever seen, every mountain, every ocean, every star in the night sky, every galaxy photographed by the Hubble Space Telescope, every atom in your body. All of that, every single bit of it, accounts for just 5% of what exists. The rest is mystery. So let's talk about that mystery. Let's talk about the things that keep physicists awake at night. The things that make astronomers re-examine their data 4, 5, 6 times because they cannot believe what they are seeing. The things that challenge not just our understanding of the cosmos, but our understanding of reality itself. And as we go through each one, I want you to really sit with the questions. Because these are not questions with easy answers. These are questions that humanity may be grappling with for centuries to come. Let us begin at the beginning. Or rather, let us begin before the beginning. Because if you want to understand the most unexplained phenomena of the observable universe, you first have to understand what the observable universe actually is, and why the word observable is itself one of the most quietly terrifying words in all of science. The observable universe is not the entire universe. It is merely the portion of the universe from which light has had enough time to reach us since the Big Bang, approximately 13.8 billion years ago. Think of it like standing in the middle of a vast ocean in thick fog. You can only see as far as the fog allows. Beyond the edge of your visibility, the ocean continues, perhaps infinitely, but you have no way of knowing what is out there. The observable universe is our bubble of visibility in a cosmos that may be, by some theoretical estimates, at least 23 trillion light-years across, or perhaps infinite. And within our observable bubble alone, there are phenomena so strange, so counterintuitive, so flat-out weird, that they challenge the very framework through which we interpret reality. And now, here is where things get interesting. Dark matter. 2 words that have haunted physics for nearly a century. The story begins in 1933 with a Swiss astronomer named Fritz Zwicky who was studying the Coma Cluster, a massive collection of galaxies roughly 320 million light-years from Earth. Zwicky was trying to measure the mass of this cluster, and he had 2 ways to do it. First, he could add up all the mass he could see, all the stars, all the visible gas, all the observable material. Second, he could measure how fast the galaxies in the cluster were moving relative to each other, because the gravitational pull holding the cluster together should correlate directly with its mass. Here is what Zwicky found. The two numbers didn't match at all. The galaxies were moving far too fast to be held together by the gravity of the visible matter alone. If only the visible matter existed, those galaxies should have flown apart long ago. They should have scattered across the cosmos like seeds in the wind. But they hadn't. They were still there, still bound together, which meant something else was there, too. Something with mass. Something with gravity. Something that didn't emit, reflect, or absorb light in any way that his instruments could detect. Zwicky called it dunkel materie, dark matter. The scientific community, for the most part, ignored him. For decades, dark matter was considered a curiosity, a calculation error, or the eccentric idea of a difficult man. And Zwicky was, by most accounts, an extraordinarily difficult man, known for insulting colleagues and dismissing critics with remarkable creativity. But the universe, in the end, vindicated him. In the 1970s, astronomer Vera Rubin was studying the rotation of galaxies, specifically the Andromeda Galaxy, our nearest large galactic neighbor, about 2.5 million light-years away. She was measuring how fast stars at different distances from the galactic center were rotating, and again, she expected a result that matched classical physics. Stars closer to the center should rotate faster, because there's more mass there, and stars further out should rotate slower, because they're farther from the gravitational center. This is exactly what happens in our solar system. Mercury zips around the Sun in 88 days, while distant Neptune takes nearly 165 years. But the galaxies didn't do this. The stars at the outer edges of galaxies were rotating just as fast, sometimes even faster, than the stars near the center. The rotation curves were flat, when physics demanded they should slope downward. And Rubin, along with her collaborator Kent Ford, confirmed this finding across dozens of galaxies, then hundreds. It wasn't a mistake. It wasn't an anomaly. It was a pattern, repeated everywhere they looked, in galaxy after galaxy after galaxy. The only explanation that fit was the same one Zwicky had proposed 40 years earlier. An enormous halo of invisible matter surrounding each galaxy, providing additional gravitational pull that kept the outer stars moving so fast. And this halo wasn't small. It was enormous, far larger than the visible disk of stars that we think of when we picture a galaxy. The dark matter halo of the Milky Way, according to current estimates, extends roughly 500,000 to over 1 million light-years from the galactic center. Our entire visible galaxy, the one we see when we look up at the night sky, is just a thin disk of stars embedded in an enormous, invisible sphere of something we cannot detect or identify. Ask yourself this question right now, and really think about it. If dark matter exists and surrounds us on all sides, passing through us every single second, why can't we detect it? What is it made of? Why does it interact with gravity but not with light? And if we can't see it or touch it, how do we know it's really there, and not just a gap in our understanding of how gravity works? These are not rhetorical questions. These are the actual questions that physicists are actively debating right now, today, in laboratories and institutions all over the world. There are several leading candidates for what dark matter might actually be. The most popular for many years was a class of particles called WIMPs, weakly interacting massive particles. The theory went that if dark matter is made of WIMPs, they should occasionally, very rarely, interact with ordinary matter through the weak nuclear force, and we might be able to detect them with sensitive enough instruments. Enormous detectors were built deep underground. The Xenon experiment in Italy's Grand Sasso Mountain, the LUX experiment in South Dakota, the PandaX experiment in China, shielded from cosmic rays by miles of rock, cooled to temperatures near absolute zero, listening for the faintest whisper of a WIMP interaction. They heard nothing. Not a single confirmed WIMP detection after decades of searching. The silence from these experiments has been deafening, and it has forced physicists to reconsider. Maybe WIMPs don't exist. Maybe dark matter is something else entirely. Axions, perhaps, which are extremely light hypothetical particles originally proposed to solve a completely different problem in physics. Or sterile neutrinos, which are theoretical cousins of the already detected but deeply strange regular neutrinos. Or perhaps dark matter is made of primordial black holes. Black holes formed in the first moments after the Big Bang, before any stars existed. Or maybe, and this is where things get really interesting, maybe dark matter doesn't exist at all. There is a school of thought, smaller but not negligible, that suggests what we're interpreting as dark matter is actually evidence that our theory of gravity is wrong. This approach is called modified Newtonian dynamics, or MOND, and it was proposed by Israeli physicist Mordechai Milgram in 1983. The idea is simple in concept but revolutionary in implication. Perhaps gravity behaves differently at extremely low accelerations, the kind found at the outer edges of galaxies, from how Newton described it. If so, then the anomalous rotation curves might not require invisible matter at all. They might simply require a modification to our gravitational equations. MOND has had some remarkable successes. It correctly predicts the rotation curves of many spiral galaxies from just their visible mass distribution, something that is genuinely impressive. But it struggles with galaxy clusters, like the ones Wiki studied, where dark matter seems to be distributed differently from the visible matter in ways that MOND cannot easily explain. And then there is the bullet cluster. The bullet cluster is one of those moments in science that feels almost theatrical in its perfection. It consists of two galaxy clusters that collided roughly 150 million years ago, about 3.7 billion light-years from Earth. When they crashed into each other, the hot gas of each cluster, the ordinary matter, smashed together, slowed down, and piled up in the middle of the collision, like two cars crashing head-on. This gas is visible in X-ray observations and sits right in the center of the collision zone. But the dark matter, inferred from gravitational lensing, the bending of light from background galaxies by mass, didn't do the same thing. It passed right through the collision, barely interacting, and ended up far ahead of the gas, on either side of the crash site. The dark matter ghosted through the collision the way two groups of people might walk through each other if they were made of pure energy. This was extraordinary confirmation that something was there, something that had mass and gravity but didn't interact with ordinary matter or light in the way the visible gas did. It was the closest thing to a smoking gun that dark matter advocates had ever seen. And for modified Newtonian dynamics, which predicts that the gravitational effects should follow the visible mass, the bullet cluster was a serious problem. And yet, the mystery deepens. Even with the bullet cluster, even with Vera Rubin's rotation curves, even with 50 years of gravitational lensing observations confirming dark matter's presence in structure after structure throughout the universe, we still don't know what it is. We can't make it in a lab. We can't catch it in a detector. We can only see its shadow, the way it bends space, the way it holds galaxies together, the way it sculpted the large-scale structure of the entire observable universe. Because here is another astonishing thing. The large-scale structure of the universe, the way galaxies are arranged into filaments and sheets and clusters, separated by vast cosmic voids, matches almost perfectly the distribution that would be predicted if dark matter exists and if it played a dominant role in the early universe, providing the gravitational scaffolding on which normal matter condensed to form the first stars and galaxies. Without dark matter, according to our best cosmological models, the universe as we see it today shouldn't exist. There wouldn't be enough gravitational pull to clump matter together fast enough after the Big Bang to form galaxies within the time available. The universe should be smooth, featureless, a thin fog of hydrogen and helium, not the spectacular, structured cosmos we observe. So dark matter, whatever it is, didn't just help shape the universe. It may have made the universe as we know it possible. Now hold on to that thought about the early universe, because we need to talk about something even more confusing. Something that isn't just unexplained, it's arguably the most embarrassing problem in all of physics. Something that was discovered by accident, has been confirmed dozens of times since, and gets stranger the more closely it is examined. It's called dark energy. In 1998, two independent teams of astronomers were studying Type Ia supernovae, exploding stars that, because they always explode with approximately the same intrinsic brightness, serve as what astronomers call standard candles. If you know how bright something actually is and you measure how bright it appears to be from Earth, you can calculate exactly how far away it is. The two teams, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were using these standard candle supernovae to measure the expansion rate of the universe at different points in time. Everyone expected the same answer. The universe had been expanding since the Big Bang, yes, but it should be slowing down. Gravity, after all, is an attractive force. All the matter in the universe is pulling on all the other matter, and that pull should be acting as a brake on the expansion. The question these teams were trying to answer was, how much is it slowing down? Is it slowing enough that the universe will eventually stop expanding and collapse back in a big crunch? Or will it expand forever, gradually decelerating but never quite stopping? What they found was neither. What they found was that the universe was not slowing down at all. It was speeding up. The expansion of the universe was accelerating. The farther away a supernova was, the more it was being carried away from us, faster and faster, as if some invisible force was pushing the fabric of space itself outward, against the inward pull of gravity. There was silence in the scientific community for a moment, followed by a collective intake of breath, followed by the kind of frenzied checking and rechecking that happens when an observation seems to contradict everything you thought you knew. But the result held. Both teams confirmed it independently. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for their discovery. The universe is not just expanding. It is accelerating its expansion, driven by some form of energy that fills all of space, that cannot be seen or directly detected, that acts in direct opposition to gravity. We call it dark energy, and we have almost no idea what it is. The most common description of dark energy invokes something called the cosmological constant, a term that Albert Einstein originally added to his equations of general relativity in 1917, when he believed the universe was static. Einstein thought the universe was neither expanding nor contracting, and he needed something in his equations to balance gravity and prevent the universe from collapsing under its own weight. He called this fudge factor the cosmological constant, represented by the Greek letter lambda. When Edwin Hubble's observations in 1929 revealed that the universe was in fact expanding, Einstein famously called the cosmological constant his greatest blunder and removed it from his equations. 70 years later, it came back. Because the cosmological constant is actually a perfect mathematical description of dark energy. It represents the energy density of empty space, the idea that the vacuum of space itself is not truly empty, but contains some inherent energy that pushes outward. In quantum field theory, this makes a certain kind of sense. Empty space at the quantum level is actually teeming with activity, with virtual particles popping in and out of existence so rapidly they cannot be directly observed, but whose collective energy contributes to the energy density of the vacuum. Here is the problem. When physicists calculate how much energy the quantum vacuum should contain, using the best tools of quantum field theory, and then compare that to the observed value of the cosmological constant that matches the observed acceleration of the universe, the numbers disagree by a factor of approximately 10 to the power of 120. Let that sink in. The theoretical prediction and the observed reality differ by 1 followed by 120 zeros. This is not a rounding error. This is not a calibration issue. This is the largest discrepancy between theory and observation in the entire history of physics. Some physicists have called it the worst prediction in the history of science. And the reason it's so troubling is not just that the number is wrong. It's that if the vacuum energy were anywhere near as large as quantum field theory predicts, the universe would have expanded so violently in its earliest moments that no galaxies, no stars, no planets, no life could ever have formed. The observed value of dark energy is small enough that the universe can exist as we see it, but the theoretical framework that should tell us what that value is gives an answer that is catastrophically, embarrassingly, universe-destroyingly wrong. What this means, in plain language, is that we do not understand empty space. We do not understand nothing. And given that space is almost entirely empty, the universe is, by volume, overwhelmingly vacuum. This means we fundamentally misunderstand the fabric of existence itself. Ask yourself this: if our best theories of physics are so wildly wrong about something as basic as the energy content of empty space, what else are we getting wrong? What other fundamental truths about reality might be completely backwards from what we currently believe? Some physicists have proposed that dark energy is not a constant at all, but varies over time, a dynamic field called quintessence, which would mean the acceleration of the universe could itself be changing. Others have proposed that our entire understanding of gravity needs to be revised on cosmological scales, just as Mond proposes for galactic scales. There are theories involving extra dimensions, theories involving modifications to general relativity, theories that invoke entirely new physical frameworks. In 2023 and 2024, data from the Dark Energy Spectroscopic Instrument, or DESI, began to hint at something genuinely startling. The dark energy might be evolving over time. The data suggested that the strength of dark energy might have been different in the past than it is today, which would be inconsistent with a simple cosmological constant. The findings were preliminary, the error bars were large, and the scientific community remained cautious, but the possibility was being taken seriously. If confirmed, it would mean that dark energy is not a fixed property of space but something dynamic, something that changes, something that might even be tied to other unknown physics. And what is dark energy doing to the universe right now? It is stretching it. Every second, the fabric of space is expanding, and galaxies that are far enough away from us, beyond a certain distance called the Hubble radius, or the cosmic event horizon, are being carried away from us faster than light can travel between us. This does not violate relativity, because it is space itself that is expanding, not anything moving through space. But the implication is deeply strange. There are galaxies out there right now that we will never see, never contact, never know about, because the space between us is expanding too fast for their light to ever reach us. They are being forever beyond the horizon of our observable universe, carried away into an unreachable darkness. And as the universe continues to accelerate, that horizon will creep closer and closer. In the extremely far future, many trillions of years from now, even the galaxies currently visible to us will have been pushed so far away by the expansion that their light will no longer reach us. The universe will become a collection of isolated islands, each galaxy unable to see or communicate with any other. In such a universe, any astronomers who might exist would look out into the sky and see nothing but darkness. They would have no way of knowing that the universe extends beyond their local group of galaxies. They would have no way of discovering cosmology as we know it, because all the evidence, all the light from distant galaxies, all the cosmic microwave background radiation would have been redshifted and stretched beyond detection. They would think they were alone in the universe, and they would be wrong. And we, today, might be in a similar position. We might think we have a handle on the universe, and we might be catastrophically wrong. Now let's talk about something that occurred before any of this, before galaxies, before stars, before atoms, before light itself. Let's talk about the very first moments of the universe's existence, and the deepest mystery embedded in the structure of time itself. When physicists model the first fractions of a second after the Big Bang, they run into something profound. According to the standard model of particle physics, matter and antimatter should have been created in exactly equal amounts. Every particle of matter, every proton, neutron, and electron should have had a corresponding antiparticle of opposite charge, an antiproton, antineutron, and positron. And when matter meets antimatter, they annihilate each other in a burst of pure energy, leaving nothing behind. This means that at the very beginning, the universe should have been a seething mix of matter and antimatter in equal amounts. And as the universe cooled, all that matter and antimatter should have met, annihilated, and left behind a universe consisting entirely of radiation, electromagnetic energy, photons, light. Nothing else. No protons, no atoms, no stars, no planets, no you. And yet, here you are. The fact that matter exists, that you exist, that galaxies exist, that anything exists at all in the universe aside from radiation, is one of the deepest mysteries in physics. It means that somehow, in the very first moments of the Big Bang, something went slightly wrong with the symmetry between matter and antimatter. Somehow, for every 1 billion antiparticles created, there were 1,000,000,001 particles of ordinary matter. The antimatter annihilated with most of the matter, leaving behind a universe flooded with radiation, and a tiny, tiny surplus of matter that survived the annihilation. That tiny surplus is everything that exists today. The question, the burning, haunting, central question of particle physics, is why? Why was there an asymmetry between matter and antimatter? Why did matter win? What physical process could have tipped the balance, even infinitesimally, in favor of the stuff that makes up reality? This is called the problem of baryogenesis, the origin of the observed excess of matter over antimatter in the universe. And it is one of the great unsolved problems in physics. We know, from experiments, that matter and antimatter are not perfectly symmetrical. There is a phenomenon called CP violation, a violation of the symmetry between particles and their mirror image antiparticles that has been observed in certain particle interactions. In the Standard Model, CP violation does occur, particularly in the behavior of particles called kaons and B mesons. But the amount of CP violation in the Standard Model is far too small, by many orders of magnitude, to account for the observed asymmetry between matter and antimatter in the universe. There must be additional sources of CP violation beyond what we currently understand, sources that lie outside our current theoretical framework. Physicists are searching for them in particle accelerators, in precision measurements of subatomic particles, in experiments designed to detect tiny differences in the properties of matter and antimatter. So far, no additional CP violation has been found. The mystery remains. And here's what makes it existentially weighted. If the asymmetry had been slightly smaller, there would be less matter today, and the universe might have been too sparse to form galaxies. If the asymmetry had been slightly larger, if the imbalance between matter and antimatter had been slightly greater, the universe might have been filled with far more matter than it is, perhaps collapsing under its own gravity before life had time to evolve. The fact that the asymmetry was exactly what it needed to be, small enough to leave a sparse but structured universe, large enough to ensure matter survived, feels in some way almost deliberate. Of course, it might not be deliberate at all. It might simply be that we live in a universe where the conditions for our existence were met, because we can only exist in a universe where they were met. This is the anthropic principle, the idea that our observations of the universe are inherently biased by the fact that we exist to make them. But the anthropic principle, while logically valid, can feel intellectually unsatisfying. It doesn't explain why the asymmetry exists. It merely explains why, if it exists, we're here to notice it. Let's shift our gaze now, from the abstract realm of particle physics to something that you can see with your naked eye on a clear night, something ancient and beautiful and strangely troubling. Look up at the night sky. Look at those stars. Now ask yourself, where did those stars come from? More specifically, where did the very first stars come from? The universe, when it was young, in its first few 100 million years, was a very different place. It was dark. After the Big Bang, the universe was filled with hot, dense plasma, a superheated mix of charged particles that scattered light constantly, making the cosmos opaque. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine and form neutral hydrogen atoms. Suddenly, light could travel freely through space, and the universe became transparent. This is the moment recorded in the cosmic microwave background radiation, the oldest light we can see, a faint glow of radiation that fills all of space and was emitted from the surface of this primordial fireball. After this, the universe entered what astronomers call the cosmic dark ages. It was filled with neutral hydrogen and helium gas, slowly drifting, slowly cooling, with no stars, no light sources, no illumination of any kind. For hundreds of millions of years, the universe was dark. And then, from the depths of that darkness, the first stars were born. These first stars, population 3 stars, as astronomers call them, were nothing like the stars we see today. They formed from gas that was almost entirely hydrogen and helium, with virtually none of the heavier elements that exist today. No carbon, no oxygen, no silicon, no iron. These elements didn't exist yet. They would have to be forged inside stars and scattered by supernova explosions. With nothing to cool the collapsing gas clouds efficiently, population 3 stars may have been enormous by today's standards. Some theorists estimate they could have had masses hundreds of times the mass of our Sun. They would have been extremely hot, extremely bright, burning furiously with a blue-white radiance, and they would have been short-lived, burning through their fuel in just a few million years before ending in catastrophic explosions. These first stellar explosions, the first supernovae in cosmic history, seeded the universe with heavy elements for the first time. They were the original alchemists, turning hydrogen into carbon, oxygen, iron, gold, and all the other elements of the periodic table, and flinging them across the cosmos. Everything you are made of, every atom in your body, was forged in the heart of a star and scattered by a stellar explosion. You are literally made of stardust. But here is the problem. We have never directly observed a population 3 star. Not one. Despite their theoretical certainty, our models of the early universe strongly predict their existence. We have never seen a confirmed example. They may have all burned out and died before we had telescopes capable of detecting them at those distances. The James Webb Space Telescope, launched in December 2021, is currently pushing back the observational frontier into those first hundreds of millions of years after the Big Bang, and it has already found galaxies far earlier than expected. Galaxies so massive and bright that they challenge our understanding of how quickly structures could form. In 2023, Webb observed galaxies from just 300 to 500 million years after the Big Bang that appear far more evolved, far more massive, and far more luminous than our models predict they should be. And the implications of this are deeply unsettling for cosmologists. The standard cosmological model, called lambda CDM, for lambda cold dark matter, is extraordinarily successful. It explains the cosmic microwave background, the large-scale structure of the universe, the abundances of light elements formed in the first minutes after the Big Bang. It is one of the great achievements of modern science. But the early universe galaxies found by Webb seem to require that those galaxies formed either faster than the model allows, or with efficiencies of star formation far higher than we think possible, or perhaps that the model itself needs revision. One possibility that has been raised, and that is being actively explored, is that dark matter in the early universe behaved differently from how it behaves today. Some models suggest that dark matter could have been warm or fuzzy in the early universe, with properties that allowed structure to form more rapidly on small scales. Other possibilities include alternative theories of gravity, early dark energy, a form of dark energy that was more active in the early universe than it is today, or even entirely new physics that we haven't yet imagined. This is the frontier. This is where science is right now. Looking at data from Webb and saying, our best model is strained. Something doesn't quite fit. And we don't know what it is. Now, from the formation of the first stars, let us leap to the most extreme objects that those stellar lives and deaths eventually produced, objects that push the laws of physics to their absolute breaking point. Objects so strange that even the people who discovered them struggled to accept they were real. Black holes. A black hole is a region of space where gravity is so intense, where mass is so concentrated that nothing can escape, not even light. The boundary of a black hole, the point of no return, is called the event horizon. Inside the event horizon, the laws of physics as we know them break down. Our equations, our theories, all the tools we use to understand the universe, simply stop working at the center of a black hole, at what mathematicians call the singularity, a point of infinite density, infinite curvature of space-time, infinite everything. When Einstein's theory of general relativity first predicted the existence of such objects in the 1910s, even Einstein himself didn't believe they were real. He thought they were mathematical artifacts, regions where the equations produced absurd results simply because the equations were being pushed beyond their range of applicability. The concept of black holes was deeply unpopular for decades, dismissed by many physicists as physically impossible. Then, in the 1960s and 70s, the evidence began to accumulate. Astronomers discovered quasars, extraordinarily luminous objects billions of light years away, pouring out more energy than entire galaxies of stars. The only mechanism that could plausibly account for their energy output was the gravitational accretion of matter onto a supermassive black hole, a black hole with millions or billions of times the mass of the Sun. Objects found in the centers of most large galaxies, including our own Milky Way. At the center of the Milky Way sits Sagittarius A*, a supermassive black hole with a mass of approximately 4 million solar masses. It is approximately 26,000 light-years from Earth. For decades, its existence was inferred from the extraordinary speed of stars orbiting around an invisible central point. The stars closest to Sagittarius A* move so fast. One star, called S2, reaches speeds of nearly 3% of the speed of light in its closest approach, that the central object's mass and compact nature became virtually undeniable. And then, in April 2019, the Event Horizon Telescope collaboration released the first image ever captured of a black hole. The supermassive black hole at the center of the galaxy M87, approximately 55 million light-years away, with a mass of 6.5 billion solar masses. It was a blurry orange ring, a halo of glowing gas surrounding a dark central void. It was one of the most iconic images in the history of science, and it confirmed, visually and directly, something that had only been inferred mathematically and through indirect observations for a century. In 2022, the same collaboration released an image of Sagittarius A* itself, the black hole at the center of our own galaxy. This was technically more difficult, because Sagittarius A* is smaller and its environment varies more rapidly than M87's, making it harder to capture a stable image. But they did it. And there it was, the black hole that sits at the heart of the Milky Way, a dark presence surrounded by a ring of light. But seeing a black hole's shadow is not the same as understanding what goes on inside one. And what goes on inside one is, to put it gently, the greatest crisis in theoretical physics today. Here is the problem. We have two extraordinarily successful theories of physics. The first is general relativity, Einstein's theory of gravity, which describes how mass curves spacetime and how matter and energy move through curved spacetime. It is tested to extraordinary precision and has passed every experimental test we have thrown at it. The second is quantum mechanics, the theory that describes the behavior of matter and energy at the smallest scales. It is the foundation of chemistry, electronics, lasers, and the modern world. It, too, is tested to extraordinary precision and has passed every test. The problem is, they're incompatible. General relativity treats spacetime as a smooth, continuous fabric. Quantum mechanics treats reality as fundamentally discrete and probabilistic. When you try to combine them, when you try to write a theory of quantum gravity, a theory that describes how gravity behaves at quantum scales, you get infinities. Nonsensical results. Equations that blow up and tell you nothing. Every attempt to merge these two frameworks has either failed or remains untested, lacking a key prediction that distinguishes it from alternatives. The place in the universe where this incompatibility is most dramatically exposed is the interior of a black hole, particularly at the singularity. At the singularity, quantum effects and gravitational effects are both enormously important, and neither theory alone is adequate. We literally do not know what happens at the center of a black hole. The honest answer is, our physics gives out. The map runs out of terrain. And making things even more confusing is what physicist Stephen Hawking discovered in 1974. Black holes aren't entirely black. Due to quantum effects near the event horizon, black holes slowly radiate energy, what is now called Hawking radiation. And over astronomically long timescales, this radiation causes the black hole to slowly lose mass and eventually, theoretically, evaporate completely. This leads to one of the most profound and contentious puzzles in physics: the black hole information paradox. In quantum mechanics, information is never destroyed. The state of a physical system can evolve over time, but in principle, you can always trace back from the final state to the initial state. The information is always preserved, just encoded differently. This is a fundamental principle called unitarity. But if a black hole evaporates completely via Hawking radiation, what happens to all the information about everything that ever fell into it? Every particle, every atom, every star that was swallowed by the black hole over its lifetime. Hawking's original calculations suggested that the radiation is perfectly thermal, essentially random, carrying no information about what fell in, which means the information is lost. But lost information violates quantum mechanics. For decades, this paradox stood as one of the central unsolved problems in theoretical physics. Hawking himself, for most of his career, argued that information was genuinely lost in black holes, that black holes represented an exception to quantum unitarity. Most quantum physicists refused to accept this. The debate was fierce, deep, and fundamental. In 2004, Hawking conceded that information is probably preserved, based on arguments from string theory and the concept of holography. The idea that the information in a volume of space is encoded on its boundary, like a two-dimensional hologram encoding a three-dimensional image. This is the holographic principle, and it suggests that the information swallowed by a black hole is somehow encoded in the Hawking radiation that comes out over the eons. But how? That's the question. The mathematical machinery that might show exactly how information is preserved in Hawking radiation is not yet fully developed. Recent work by physicists including Ahmed Almhiri, Donald Merolf, and others has introduced new concepts: entanglement wedges, quantum extremal surfaces, the island formula, that suggest information is preserved, but through mechanisms so exotic that they imply radical new views of space-time geometry. Some of this work suggests that the interior of a black hole might be geometrically connected to the exterior radiation via quantum entanglement in ways that have no classical analog, that the interior of the black hole might, in some sense, not even be a separate region of spacetime but rather a sort of quantum entangled construct. The implications of this, if correct, go far beyond black holes. They suggest that spacetime itself, the fabric of reality that we move through, might be an emergent property of quantum entanglement. That spacetime is not fundamental, but is built from something deeper. The quantum correlations between microscopic degrees of freedom that we don't yet fully understand. This is, to put it mildly, a radical idea, and it is being taken seriously by some of the most prominent theoretical physicists in the world. Ask yourself, if spacetime itself is not fundamental, if it emerges from something more basic, then what is reality at the deepest level? What is the universe actually made of? Nobody knows. But while physicists wrestle with the interiors of black holes, there is another kind of extreme phenomenon in the universe that is perhaps even more dramatic in its observational signature, even more violent in its physics, even more laden with mystery. It is brief. It is brilliant. It is the most powerful explosion in the cosmos since the Big Bang. It is a gamma-ray burst. Gamma-ray bursts, GRBs, are intense flashes of gamma radiation, the most energetic form of electromagnetic radiation that arrive from deep in the universe with no warning. They are, while they last, the most energetically luminous events in the observable universe. A single gamma-ray burst can, in a matter of seconds or minutes, release more energy than the sun will emit over its entire 10 billion year lifetime. Some bursts release more energy in a few seconds than our entire Milky Way galaxy will emit in 10,000 years. They were discovered by accident. In the 1960s and 70s, the United States was operating a series of satellites called Vela, designed to detect nuclear tests in violation of the Nuclear Test Ban Treaty. These satellites were looking for gamma-ray flashes that would indicate nuclear explosions in space, a concern at the height of the Cold War. The satellites did detect gamma-ray flashes, lots of them, but they weren't coming from Earth or the Soviet Union or anywhere in our solar system. They were coming from random directions in deep space. The discovery was classified for years. When it was finally declassified and shared with the scientific community in 1973, it sparked one of the longest-running mysteries in modern astronomy. For 20 years, the origin of gamma-ray bursts was completely unknown. Were they nearby, in the Milky Way? Were they far away, in the distant universe? Because nobody knew their distances, nobody could calculate their energies, and the hypotheses ranged from nearby collisions of comets to exotic physics in the cores of distant galaxies. The answer, confirmed definitively in the late 1990s, was that most gamma-ray bursts are very far away, billions of light years, which means the energy involved is almost incomprehensible. Today, we know that there are two main types of gamma-ray bursts. Long gamma-ray bursts, lasting more than 2 seconds, are thought to occur when a massive star collapses into a black hole or neutron star, a process called a collapsar. The collapsing core shoots out two incredibly powerful jets of matter and radiation at speeds close to the speed of light, and it is the interaction of these jets with surrounding material that produces the gamma rays. Short gamma-ray bursts, lasting less than 2 seconds, are thought to be produced by the merger of two compact objects, two neutron stars, or a neutron star and a black hole, spiraling into each other over billions of years before finally coalescing in a cataclysmic event. And this brings us to one of the most extraordinary observational moments in modern astronomy: the detection of GRB 170817A, which was coincident with a gravitational wave signal detected on August 17, 2017. But wait, we've jumped ahead. To fully appreciate that moment, we need to talk about gravitational waves. Gravitational waves are ripples in the fabric of space-time, produced by the acceleration of massive objects. Einstein predicted them in 1916 as a consequence of general relativity. When two massive objects, say, two black holes, orbit each other, they should distort space-time as they move, sending ripples outward through the cosmos at the speed of light. These ripples stretch and squeeze space itself as they pass, alternately lengthening and shortening distances in perpendicular directions by incredibly tiny amounts. For decades, gravitational waves were predicted but never detected. The strains involved, the fractional changes in distance, were predicted to be so small that detecting them seemed almost impossible. For a gravitational wave produced by two black holes merging at a distance of 1 billion light-years, the expected strain is on the order of 10 to the negative 21. That means, for a detector 4 kilometers long, the expected displacement is about 1/10,000th the diameter of a proton. Building an instrument sensitive enough to detect this required decades of technological development and an extraordinary engineering achievement. The Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO consists of two identical detectors, one in Hanford, Washington, and one in Livingston, Louisiana, each consisting of an L-shaped vacuum tube 4 kilometers long, through which a precisely calibrated laser beam bounces back and forth. When a gravitational wave passes, the arms of the L change length by that almost unimaginably tiny amount, and the interference pattern of the laser light shifts. On September 14, 2015, LIGO detected its first gravitational wave signal. It had come from the merger of two black holes, approximately 1.3 billion light-years away. The signal, called GW150914, lasted just a fraction of a second in the sensitive frequency band of the detector, but it was unmistakable. It was the first direct detection of gravitational waves, confirming a key prediction of general relativity exactly 100 years after Einstein had first proposed it. The LIGO team, along with European collaborator Virgo, received the Nobel Prize in Physics in 2017. But the most scientifically spectacular gravitational wave event came on August 17, 2017. LIGO and Virgo detected a signal from the merger of two neutron stars, GW170817, from a distance of approximately 130 million light-years. Neutron star mergers are much less energetic than black hole mergers, but they produce something that black hole mergers apparently do not: light. Electromagnetic radiation across many wavelengths. And approximately 1.7 seconds after the gravitational wave signal arrived, gamma-ray observatories detected a short gamma-ray burst from the same location. For the first time in history, the same cosmic event had been observed in both gravitational waves and electromagnetic radiation simultaneously. This was the birth of what astronomers call multi-messenger astronomy, looking at the universe not just with light but with gravitational waves, neutrinos, and other messengers. The neutron star merger, now called a kilonova, was observed by dozens of telescopes across the entire electromagnetic spectrum, from radio waves to gamma rays, and it confirmed long-standing theories about neutron star mergers. It also revealed something astonishing. Neutron star mergers are the forge where some of the heaviest elements in the universe, gold, platinum, uranium, and others, are produced. The gold in your rings, the platinum in your jewelry, the uranium in nuclear reactors, forged in the catastrophic merger of neutron stars billions of years ago. And yet, even these confirmed discoveries leave profound mysteries behind. Like, what exactly is a neutron star? A neutron star is the collapsed remnant of a star that exploded as a supernova. When the core of a massive star collapses, if it doesn't have enough mass to form a black hole, the collapse is halted by the pressure of neutrons packed so tightly they literally cannot be compressed further without violating the Pauli exclusion principle, the quantum mechanical rule that no two identical fermions can occupy the same quantum state. The result is an object with roughly 1.5 times the mass of the Sun, compressed into a sphere about 20 kilometers in diameter. Think about that. The mass of 1.5 suns in something the size of a city. The density of a neutron star is almost incomprehensible. Approximately 400 trillion times the density of water. A teaspoon of neutron star material would weigh roughly 400 million metric tons. The gravity at the surface of a neutron star is about 200 billion times Earth's surface gravity. An astronaut at the surface of a neutron star would be compressed by gravity into a layer roughly 1 atom thick. The interior of a neutron star is one of the great unknowns of physics. The outer layers are composed of ordinary atomic nuclei arranged in a crystalline lattice, a solid crust. Deeper in, the density becomes so extreme that nuclei dissolve into a fluid of free neutrons. And at the very core, where the density exceeds the density of an atomic nucleus itself, something happens that we don't understand. The matter may transition into exotic states that have no analog anywhere else in the universe. There might be a quark-gluon plasma, a state where quarks are no longer confined inside protons and neutrons but float free. There might be strange quark matter, or what is sometimes called strange matter, made of 3 types of quarks rather than the 2 types, up and down, that compose ordinary nuclear matter. There might even be kaon condensates or other exotic phases of matter predicted by nuclear physics but never directly observed. We genuinely don't know what sits at the heart of a neutron star. The extreme pressures and densities there are beyond anything we can recreate in any laboratory on Earth. And our theories of nuclear and quark matter are extrapolations into territory where they have never been tested. And then there are pulsars, rapidly rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As the star rotates, the beam sweeps across the sky like a lighthouse, and if the beam sweeps past Earth, we detect regular pulses of radiation with extraordinary precision. The Crab pulsar, for example, rotates 33 times per second, and the fastest pulsars known, called millisecond pulsars, rotate hundreds of times per second. The fastest ever detected, PSR J1748-2446 AD, rotates approximately 716 times per second. That is an object the size of a city, with roughly 1.5 times the mass of the Sun, spinning 716 times every single second. At its equator, the surface is moving at approximately 24% of the speed of light, and it maintains this rotation with extraordinary stability. The best pulsars are more accurate timekeepers than atomic clocks. Some pulsars are so stable that astronomers have used arrays of them, called pulsar timing arrays, to search for gravitational waves passing through our galaxy, with recent results in 2023 providing the first evidence for a gravitational wave background permeating the entire galaxy, produced by the slow spiraling of supermassive black hole binaries in distant galaxies. Pulsars are extraordinary, and yet they, too, harbor mysteries. What exactly is the equation of state of the matter inside them? How do their magnetic fields generate the beams of radiation? Why do some pulsars occasionally glitch, suddenly speeding up their rotation, as if something slipped inside the star? These glitches are thought to involve the superfluid interior of the neutron star, where vortices of rotating quantum fluid transfer angular momentum to the crust. But the details remain poorly understood, and the exotic physics of the neutron star interior remains one of the most active and unsettled areas of research in astrophysics. Before we move on to the next great mystery, let's pause for a moment and sit with the enormity of what we've discussed so far. Dark matter, making up roughly 27% of the universe's total energy content, gravitationally sculpting every galaxy and galaxy cluster in the observable cosmos, and completely unidentified despite decades of searching. Dark energy, making up roughly 68% of the universe's total energy content, driving the acceleration of cosmic expansion, described mathematically by a term Einstein invented and then abandoned, and understood so poorly that our best theoretical prediction of its magnitude is wrong by 120 orders of magnitude. The matter-antimatter asymmetry, which is the reason anything exists at all, and which our best particle physics cannot explain. The first stars, predicted but never observed, whose legacy is woven into every atom of your body. Black holes, whose interiors represent a total breakdown of our physical theories, and whose relationship to quantum information challenges the nature of space-time itself. Gamma-ray bursts, the most violent explosions in the cosmos, forging the gold in our jewelry in the death screams of neutron stars. And gravitational waves, ripples in space-time itself, now a new sense with which we can perceive the universe. And we're just getting started. Let's talk about something much closer to home, cosmically speaking. Something in our own galaxy that has puzzled astronomers for decades and that sits right at the heart of what we think we know about how the universe works. In 2007, an astronomer named Duncan Lorimer and his student David Narkevic were sifting through archival data from the Parkes Radio Telescope in Australia, searching for pulsars. Buried in data from 2001 was something extraordinary. A single, incredibly bright burst of radio waves that lasted only a few milliseconds. It had a characteristic signature, called dispersion, the way higher frequency radio waves travel faster than lower frequency ones through the intergalactic medium, that indicated it had traveled an enormous distance, far outside our galaxy, billions of light years away. It was brief, it was bright, it was isolated, and nothing like it had ever been seen before. Lorimer and Narkevic reported their finding in 2007, and it was largely greeted with skepticism. An isolated millisecond burst of radio waves from billions of light years away, with an energy equivalent to the energy output of the sun over 3 days, all released in a few milliseconds. It seemed impossible. Many astronomers assumed it was terrestrial interference, some kind of local radio frequency contamination, or a glitch in the data. It was called the Lorimer burst, and it sat in relative obscurity. Then more were found. Not many, but enough. A handful of similar events, all brief, all bright, all apparently from cosmological distances, all completely unexplained. They were given a name, fast radio bursts, or FRBs. And then, in 2016, something changed. A fast radio burst was found to be repeating, sending out bursts at irregular intervals from the same location in the sky. This was dubbed FRB 121102, located in a small dwarf galaxy about 3 billion light-years from Earth. A repeating FRB was doubly astonishing, because it ruled out explanations that required the source to be destroyed in the process of producing the burst. Something was there, sending out these screams of radio waves repeatedly, from billions of light-years away. The source of FRB 121102 was eventually localized to an active region within that dwarf galaxy, and associated with a persistent, compact radio source. Possibly a neutron star in an extreme environment, surrounded by unusually dense plasma. But the mechanism by which any object could produce bursts of this intensity from such a distance remains deeply uncertain. Today, hundreds of fast radio bursts have been detected, thanks in large part to the Canadian Hydrogen Intensity Mapping Experiment, CHIME, a radio telescope in British Columbia specifically designed to detect them. Most are one-off events, non-repeating. A few repeat. They appear to come from all over the sky, from many different types of galaxies. In April 2020, a fast radio burst was detected from within our own Milky Way, from a magnetar called SGR 1935 plus 2154, confirming that at least some FRBs are produced by magnetars, which are neutron stars with extraordinarily powerful magnetic fields. But whether all FRBs are produced by magnetars, or whether there are multiple source populations, remains an open question. Magnetars are themselves remarkable objects. Their magnetic fields are the strongest known in the universe, roughly 1 quadrillion times stronger than Earth's magnetic field. At such field strengths, the quantum vacuum itself becomes significantly affected. A magnetar's magnetic field is strong enough to distort the electron shells of atoms, changing their chemical properties, and at very close range it would affect even the geometry of spacetime. The energy stored in a magnetar's magnetic field is so enormous that when it is released, in a process called a starquake or a magnetic reconnection event, it can produce enormous bursts of X-rays and gamma rays. One such event, from a magnetar called SGR 1806-20 on December 27, 2004, briefly outshone the full moon and was detectable by instruments designed to study the sun's solar flares, despite the magnetar being 50,000 light-years away. The burst was so intense that it ionized the upper atmosphere of Earth, perturbing long-wave radio communications. An event like this from within a few hundred light-years of Earth would be catastrophic. But while magnetars may explain some fast radio bursts, the most energetic and most distant ones remain puzzling. How can a single object produce a burst carrying the energy equivalent of days or weeks of solar output, released in milliseconds, from billions of light-years away? The physical processes involved, whatever they are, must be extraordinarily efficient, converting enormous amounts of energy into coherent radio waves at a level that seems to strain physical plausibility. There have even been, inevitably, more exotic proposals. Some researchers have suggested that extremely advanced technological civilizations, alien intelligence, might produce signals that look like fast radio bursts. Harvard astrophysicist Avi Loeb has been particularly vocal in keeping this possibility open, arguing that we should not dismiss extraordinary sources until we have ruled them out by careful scientific investigation. Most astrophysicists consider this highly unlikely compared to natural astrophysical explanations. But the fact that we still don't fully understand FRBs means we can't completely close the door on any idea. And speaking of extraordinary signals from the cosmos, we cannot talk about the unexplained phenomena of the observable universe without addressing what is perhaps the most famous unexplained signal in the history of radio astronomy: the WOW signal. On the night of August 15, 1977, astronomer Jerry Eman was working with a Big Ear radio telescope at Ohio State University as part of the SETI Search for Extraterrestrial Intelligence project. Eman was reviewing computer printouts of radio signals received from space, looking for anything unusual. Most of the printouts were filled with low-level noise, the natural static of the cosmos. But on this particular night, on this particular printout, there was something different. A sequence of letters and numbers, 6EQUJ5, representing a signal that rose dramatically in intensity, peaked, and then fell off over the course of 72 seconds in a pattern perfectly consistent with what would be expected from a narrowband radio signal from a fixed point in the sky, observed as the Earth's rotation carried the telescope beam across it. The signal was extraordinary. It was at a frequency very close to 21 centimeters, the wavelength at which neutral hydrogen emits radiation, a frequency that many SETI researchers had long suggested any intelligent civilization trying to communicate might choose because of its cosmic significance and ubiquity. The signal was narrowband, more concentrated than any known natural source of radio emission, and it had appeared only once, from the direction of the constellation Sagittarius, from somewhere beyond our solar system. Eman circled the sequence and wrote, "Wow," in the margin of the printout. And that is what it has been called ever since. Despite decades of follow-up observations using many different radio telescopes, the WOW signal has never been detected again. No natural explanation has been firmly established that accounts for all of its characteristics. Proposed natural explanations include a passing comet, a hypothesis proposed in 2016 that was subsequently challenged by other researchers who pointed out the comet in question, 266P/Christensen, did not match the observed signal characteristics. Other proposals include interstellar scintillation, which is a kind of radio twinkling that can briefly amplify a weaker signal. But none of these fully satisfies the scientific community. Was the WOW signal a message from an extraterrestrial intelligence? Probably not. The scientific consensus is that we shouldn't jump to that conclusion without much more evidence. But it was something. Something real, something unusual, something that hasn't been explained. And after 47 years, it remains the single most compelling candidate for an unusual radio signal ever received. Now, while we're in the territory of things that have been detected but not understood, let me tell you about something much larger than a radio burst. Something that sits at the intersection of cosmology and the deepest confusion. Something called the cold spot. The cosmic microwave background radiation, the CMB, is the faint afterglow of the Big Bang, the radiation emitted when the universe became transparent about 380,000 years after its birth. It fills the entire sky, in every direction, with almost perfect uniformity. Its temperature is approximately 2.7 Kelvin everywhere you look, but not perfectly uniform. There are tiny fluctuations, ripples in temperature of about 1 part in 100,000, that correspond to tiny density variations in the early universe. These fluctuations are the seeds of all large-scale structure. The regions of slightly higher density that, over billions of years, collapsed under gravity to form galaxies and galaxy clusters. These fluctuations in the CMB have been mapped with extraordinary precision by satellites including COBE, WMAP, and Planck, and their statistical properties match with remarkable precision the predictions of the lambda CDM model. Almost. Because there are features of the CMB that don't quite fit, and one of them is particularly striking. In the southern sky, there is a region of the CMB that is significantly colder than the statistical average, about 70 microkelvin colder than expected, over a patch of sky about 10 degrees across. This is the cold spot. It was first identified in data from the WMAP satellite in 2004 and confirmed by the Planck satellite subsequently. Its existence is a statistical anomaly, not impossible, but unlikely to occur by chance given our models of how the CMB fluctuations should be distributed. Several explanations have been proposed. One is simply statistical chance. Given the finite amount of sky, unusual features are expected to appear occasionally, and the cold spot might just be an extreme end of a normal distribution. Another is a systematic error or artifact in the data, though this has been carefully ruled out by the satellite teams. And then there is the more exotic explanation, a supervoid. The cold spot might be caused by an enormous region of space along our line of sight that is significantly emptier than average. A cosmic void so large, perhaps 700 to 1,000 megaparsecs across, that photons from the CMB, upon passing through it, lose a tiny amount of energy via a mechanism called the integrated Sachs-Wolf effect. And indeed, surveys of galaxies in the direction of the cold spot have found evidence for an underdense region, a large void, in the appropriate location. But the supervoid explanation requires a void so large and so empty that it strains the predictions of lambda CDM. Voids of that size and depth are expected to be very rare in our models of cosmic structure. And some analyses suggest that even with a supervoid, the full depth of the cold spot cannot be explained. There must be additional physics at work. And this is where theorists have gotten genuinely creative, the cold spot might be evidence of a cosmic collision. In the multiverse theory, the idea that our universe is just one of countless bubble universes in a much larger cosmic sea, it has been proposed that our universe might have collided with a neighboring bubble universe in its very early history, leaving an imprint on the CMB. This imprint might appear as a cold spot, or a circular feature in the CMB temperature map. This is, to be clear, highly speculative. The multiverse remains a theoretical construct without direct observational confirmation. But the multiverse is a natural consequence of several well-motivated physical theories, including eternal inflation, the idea that the inflationary expansion of the early universe never fully stopped, but continues in some regions of space even today, creating new bubble universes in a never-ending process of cosmic reproduction. In this framework, our universe is just one bubble among an infinite sea of bubbles, each with potentially different physical constants, different laws, different possibilities. And if the multiverse exists, then almost anything becomes possible. And at the same time, almost nothing becomes truly explainable, because any set of physical laws can be realized somewhere, and the selection effects that govern which universe we find ourselves in may be far more complicated than we can even conceptualize. Let's now turn to something even more fundamental, something that sits at the very heart of our understanding of reality, and that has been a source of philosophical and scientific bewilderment since it was first discovered in the 1920s. Something that tells us, in no uncertain terms, that the universe is fundamentally stranger than we could have imagined. Quantum mechanics. I know what you might be thinking. Quantum mechanics isn't exactly an unexplained phenomenon. It's a well-developed physical theory with extraordinary predictive power. And you'd be right. Quantum mechanics is perhaps the most precisely tested theory in the history of science. Its predictions have been verified to more than 10 decimal places in some cases. It underlies all of chemistry, solid-state physics, nuclear physics, and particle physics. Without quantum mechanics, nothing electronic would work. No computers, no smartphones, no lasers, no LED lights. But here's the thing. Quantum mechanics works. We just don't know why. We don't know what it means. We don't understand it at a deep, interpretational level. And this is not a trivial complaint. It is one of the most profound open questions in all of human thought. Quantum mechanics tells us that before a measurement is made, a quantum system does not have a definite state. An electron doesn't have a definite position, or a definite momentum, or a definite spin. It exists in a superposition of all possible states simultaneously, described by a mathematical object called a wave function. When a measurement is made, the wave function collapses to one definite outcome, but which outcome, even in principle, cannot be predicted in advance. Only the probabilities of different outcomes can be calculated. This is deeply, profoundly strange. It means that the universe, at its most fundamental level, is not deterministic. The future is not fully determined by the past, even in principle. There is irreducible randomness baked into the foundations of reality. But it gets stranger. One of the most startling features of quantum mechanics is entanglement. When two quantum particles interact, they can become entangled, correlated in such a way that measuring the state of one particle instantaneously determines the state of the other, no matter how far apart they are. Measure the spin of one entangled particle and find it pointing up, and you immediately know the spin of the other is pointing down, even if the other particle is on the other side of the galaxy. This was what Einstein famously called spooky action at a distance, and he deeply disliked it. He believed it meant quantum mechanics was incomplete, that there must be hidden variables underlying the quantum description of reality, variables that predetermine the outcomes and just haven't been discovered yet. In 1935, he, Boris Podolsky, and Nathan Rosen published a famous paper, known by the initials of its authors as the EPR paper, arguing that quantum mechanics must be incomplete precisely because of entanglement. In 1964, physicist John Bell derived a mathematical theorem, Bell's inequality, that showed how to test experimentally whether the correlations observed in entangled particles are consistent with hidden variables or not. If hidden variables exist, Bell showed, the correlations between measurements of entangled particles cannot exceed a certain value. If quantum mechanics is correct, those correlations can exceed that value. The experiments, performed first by John Clauser in the 1970s and then with increasing precision by Alain Aspect in the 1980s, and many subsequent groups since, have consistently found that the Bell inequalities are violated. The correlations are stronger than any hidden variable theory can produce. The universe is not hiding classical variables underneath quantum mechanics. The universe is genuinely, irreducibly quantum. In 2022, Alain Aspect, John Clauser, and Anton Zeilinger were awarded the Nobel Prize in Physics for this work. What this means is staggering. The correlations between entangled particles cannot be explained by any classical mechanism. They cannot be pre-programmed. The particles don't decide their outcomes before the measurement, because the measurement choice can be made at the last instant, and the correlations still appear. They cannot be explained by signals passing between the particles, because that would require the signal to travel faster than light, which contradicts special relativity. And yet the correlations are there. The correlations are real. They happen every time. And we cannot explain them in terms of any underlying reality that we understand. The philosopher's question that quantum mechanics forces upon us is, what is happening when nobody is looking? When a quantum particle is not being measured, does it even have definite properties? If a tree falls in a forest and nobody is there to observe it, does it make a sound? In quantum mechanics, the answer might literally be, not only does it not make a sound, it might not even fully exist until the observation is made. There are many interpretations of quantum mechanics that attempt to make sense of this. The Copenhagen interpretation, associated with Niels Bohr, says that asking what happens between measurements is meaningless. Reality is what we measure, and the question of an underlying reality independent of measurement is simply not scientific. The many worlds interpretation, proposed by Hugh Everett in 1957, says the wave function never collapses at all. Instead, every time a quantum measurement is made, the universe splits into multiple branches, each containing one of the possible outcomes. In this view, there are an infinite number of parallel universes, each equally real, each containing a different version of history. The pilot wave theory, developed by David Bohm, restores determinism, but at the cost of introducing a mysterious wave that guides particle trajectories in a non-local way. The relational interpretation, associated with Carlo Rovelli, says that quantum states are not absolute but are always defined relative to a particular observer. Each of these interpretations makes the same predictions as standard quantum mechanics. They are empirically equivalent, which means there is no experiment that can currently distinguish between them. The choice of interpretation is a philosophical choice, not a scientific one, and many physicists simply choose not to think about it, to apply the formalism of quantum mechanics and not ask what it means, in the pragmatic spirit of shut up and calculate. But the question of what quantum mechanics means, what reality is actually like at the deepest level, is not going away. And the resolution of this question may be intimately connected to the resolution of the incompatibility between quantum mechanics and general relativity, to the nature of dark matter and dark energy, to the arrow of time, and to perhaps the deepest mystery of all, why there is something rather than nothing. The arrow of time. Let's talk about this, because it is one of those things that seems so obvious it shouldn't be mysterious, and yet when you look at it carefully, it is one of the most baffling aspects of reality. Time flows in one direction. You remember the past. You don't remember the future. Eggs break but don't unbreak. Ice melts but doesn't spontaneously refreeze. Stars are born, age, and die. They don't run backwards, reabsorbing radiation and reconstituting themselves from ash. In everyday experience, there is a clear and unambiguous arrow of time, pointing from past to future. And yet, the fundamental laws of physics, Newton's laws, Maxwell's equations, quantum mechanics, general relativity, are all time-symmetric. They work equally well in both temporal directions. If you watched a movie of two billiard balls colliding and run the movie backwards, you cannot tell which direction is the real one. Both are physically possible. At the microscopic level, the laws of physics make no distinction between forward and backward in time. So where does the arrow of time come from? Why does the universe have a past and a future that are so different from each other? The standard answer invokes entropy, the second law of thermodynamics. Entropy is a measure of disorder, and the second law says that entropy increases over time. Systems evolve from ordered states to disordered states. A glass falls and shatters, its entropy increases. A gas expands to fill a container, its entropy increases. The entropy of the universe as a whole increases over time, and this increase defines the arrow of time. But this only pushes the question back. Why did the universe start in a low entropy state? Why was the early universe, just after the Big Bang, so extraordinarily ordered and uniform? The Big Bang represents the lowest entropy state the universe has ever been in, and from that starting point, entropy has been increasing ever since. But why did the universe start with low entropy? What set the initial conditions that way? The physicist Roger Penrose has estimated the probability of the universe starting in the state it did. The precise low-entropy state required for the universe as we observe it, as being on the order of 1 in 10 to the power of 10 to the power of 123. That is not a misprint. It is a number so vastly, incomprehensibly small that it makes any other probability you have ever thought about seem like a near certainty by comparison. Some cosmologists have proposed that the low entropy of the Big Bang is not an initial condition that needs explaining within our universe, but rather a consequence of some larger scale structure. Perhaps a multiverse in which our universe is simply one of many, with different initial conditions, and we inevitably find ourselves in a universe with low enough initial entropy for structure to form and life to evolve. But this again invokes the multiverse, which is untestable by current methods. Others have suggested that the arrow of time is cosmological in origin, that it reflects the expansion of the universe, and that in a hypothetical contracting universe, the arrow of time might run in the opposite direction, though this is not well established. Still others suggest that time itself is emergent, that it does not exist at the fundamental level of physics, but arises from the statistical behavior of many quantum degrees of freedom, much as temperature arises from the microscopic motion of atoms. And some physicists, most notably Julian Barber in his book, The End of Time, have argued that time does not exist at all, that what we call time is a human interpretation of the relative configurations of physical systems, and that the universe at its deepest level is timeless, a static landscape of all possible configurations, with no flow, no past, no future. If that sounds like something from a science fiction novel, that's because we're genuinely in territory where the distinction between physics and philosophy becomes blurry. And that is uncomfortable for scientists who like clear boundaries. But reality, apparently, does not care about what makes us comfortable. Now let's talk about something that is both deeply technical and deeply haunting. Something that might be the most important unresolved question in all of fundamental physics, and that touches on whether our universe is the only one that could possibly exist. Why are the constants of nature the values they are? The universe is governed by a set of fundamental constants, numbers that appear in the equations of physics and that we measure but do not derive from first principles. The speed of light, c. Planck's constant, h. The gravitational constant, g. The charge of the electron. The masses of the quarks. The strength of the strong nuclear force. The weak nuclear force, electromagnetism. The cosmological constant, or the energy density of dark energy. These numbers are what they are. We measure them. We don't know why they have the values they have, and we can't derive them from any deeper principle within our current theoretical framework. They are, in a profound sense, given initial data, inputs to the system of physics, not outputs. But here's the breathtaking thing. If these constants were even slightly different, the universe as we know it could not exist. And I don't mean we'd have a slightly different universe with different kinds of life. I mean the universe would be completely unlivable. Often, it wouldn't even have atoms, or stars, or galaxies. If the strong nuclear force were slightly weaker, atomic nuclei would be unstable and atoms couldn't exist. The universe would be a sea of free protons, unable to form any chemistry. If it were slightly stronger, all the hydrogen in the early universe would have fused into helium, with no hydrogen left over, and stars like the Sun, which burn hydrogen and produce the stable, long-lived warmth that allows life to evolve, could not exist. If the electromagnetic force were slightly different in relation to the strong nuclear force, the chemistry of carbon, which is the basis of all known life, would be disrupted. Carbon is produced in stars through a process called the triple alpha process, which requires an almost miraculous resonance between the energy levels of helium and carbon nuclei. Physicist Fred Hoyle famously predicted this resonance before it was measured, reasoning that carbon-based life exists. Therefore, the resonance must exist. When the resonance was measured and found, it was at almost exactly the predicted value. Hoyle called this one of the most improbable things he had ever encountered, and it led him to speculate about some form of cosmic intelligence or intention, a remarkable admission from an avowed atheist. If gravity were slightly stronger, stars would burn through their fuel much faster, and the universe would have no time to produce complex chemistry and life. If it were slightly weaker, stars might not form at all. If the cosmological constant, the strength of dark energy, were slightly larger, the universe would have expanded too fast for galaxies to form. If it were large but negative rather than positive, the universe would have collapsed back in a big crunch within seconds of the Big Bang. The value of the cosmological constant seems exquisitely tuned to a value that allows a long-lived, structured universe. These apparent coincidences are what physicists call the fine-tuning problem. And there are essentially two ways to approach it. Either the constants are what they are for a reason. Perhaps a deeper theory will explain why they have to have these values. Or they are what they are because we exist to observe them, in a universe that was the one random instance among many that happened to have the right combination of constants. The second approach requires the multiverse. If there are an enormous or infinite number of universes, each with different values of the physical constants, then by pure chance some of them will have constants compatible with the existence of observers. And we, inevitably, find ourselves in one of those universes. This is called the anthropic reasoning. The problem with anthropic reasoning is that it's not entirely scientific. It can't be tested, at least not with current technology. And it can feel like giving up, like saying, why is the universe the way it is? Because otherwise you wouldn't be here to ask. It is logically valid, but it is deeply unsatisfying, and it closes off the possibility of a deeper explanation. The other approach, searching for a deeper theory that explains why the constants must have the values they do, is the dream of theoretical physics. Einstein spent the last decades of his life searching for a unified field theory that would explain all the forces and constants of nature as aspects of a single, deeper framework. String theory, or more precisely, superstring theory and M-theory, is the current leading candidate for such a unified framework. It is a mathematical framework in which the fundamental objects are not point particles but one-dimensional strings, vibrating at different frequencies to produce different particles. String theory naturally incorporates both quantum mechanics and general relativity, and it potentially could explain the values of the fundamental constants as arising from the geometry of extra dimensions that are too small to observe directly. But string theory has a serious problem: the landscape. It turns out that string theory doesn't predict a unique universe. It predicts an enormous number of possible universes. Estimates put the number at something like 10 to the power of 500. Each with different values of the physical constants, each corresponding to a different solution to the equations. Rather than predicting that the constants must be precisely what they are, string theory seems to allow almost any combination. The specific universe we observe is just one point in this vast landscape of possibilities. This is either a deep problem with string theory, a sign that it is too flexible and not predictive enough, or it is a profound insight. The string theory landscape is the theoretical underpinning of the multiverse. Each of those 10 to the 500 solutions corresponds to a different bubble universe in a multiverse, and we find ourselves in the one whose constants are compatible with our existence. There is no consensus on which of these views is correct. String theory remains mathematically beautiful and incredibly productive. It has generated extraordinary insights in pure mathematics and theoretical physics, but it has not produced a single falsifiable prediction that has been experimentally tested. After 50 years of development, this is a serious concern, and some physicists, Lee Smolin and Peter Woit being the most prominent critics, have argued that string theory is not science in the traditional sense because of its inability to be experimentally tested. The debate over string theory, the multiverse, and the nature of scientific explanation is one of the deepest and most contentious in modern physics. And it may not be resolvable with current or even foreseeable technology. Let's step back now from the very large and the very theoretical and turn to something that is in some ways more intimate: A mystery that sits not in the distant cosmos, but right here, in our local corner of the universe, something you can almost see with your naked eye on the right kind of night.
The Milky Way, our galaxy.
Home to somewhere between 100–400 billion stars, and according to the best current estimates from Kepler telescope data and statistical analysis, many more planets than that, possibly 1 trillion or more. And on at least one of those planets, this one, intelligent life evolved, looked up at the night sky, and began to wonder. Which raises what is perhaps the most personal and immediate of all cosmic mysteries. Where is everyone else? This is the Fermi paradox, named after physicist Enrico Fermi, who supposedly raised it in a casual conversation at Los Alamos National Laboratory in 1950, though the exact details of that conversation are disputed. The paradox goes like this. The universe is approximately 14 billion years old. Our galaxy alone contains hundreds of billions of stars. Many of those stars have planets. Many of those planets are in habitable zones, at the right temperature for liquid water to exist. Given the enormous number of opportunities for life to arise, and given the vast amount of time available, and given that even a civilization traveling at just 1% of the speed of light could colonize the entire Milky Way in about 10 million years, a blip in cosmic time, where are all the aliens? Why haven't we detected radio signals? Why haven't we seen megastructures? Why, when we look out into the universe, do we see an extraordinary cosmos of stars and galaxies and phenomena, but no sign, zero sign, of any other civilization? The silence is deafening, and it demands explanation. The solutions proposed to the Fermi paradox are numerous, and many of them are deeply unsettling. Here are some of the most discussed, and I want you to think about which one you find most compelling or most troubling. The first solution is simply that we are alone. Life is extraordinarily rare, perhaps even unique to Earth. Despite the enormous number of planets, the conditions required for life to arise, the right chemistry, the right energy sources, the right geological stability, the right cosmic environment, might be so improbable that only one world in the entire observable universe has managed to produce it. Or perhaps life arises often, but intelligent life is extraordinarily rare. Perhaps the emergence of complex, multicellular life, or the development of nervous systems, or the origin of language and technology, requires a sequence of such unlikely steps that it has happened exactly once. This is sometimes called the rare Earth hypothesis, laid out in detail by Peter Ward and Joe Kirschvink in their 2000 book. The second solution is the Great Filter. Perhaps civilizations do arise throughout the universe, but at some point in their development, they inevitably encounter a catastrophic obstacle, a great filter, that prevents them from expanding into the cosmos. The question, then, is whether the Great Filter is behind us or ahead of us. If the filter is the origin of life, a step so improbable that it almost never happens, then it's behind us, and we're one of the rare successes. If the filter is the transition from single-celled to multi-celled life, or the development of intelligence, then again, it might be behind us. But if the filter is ahead, if civilizations inevitably destroy themselves through war, disease, climate change, advanced AI, or some other technology before they can spread to other stars, then the silence of the cosmos is a grim omen. It might mean that we, too, are approaching the filter and will fail to pass it. This is one of the reasons some scientists argue that if we discover simple life elsewhere in the solar system, in the oceans beneath the ice of Europa or Enceladus, or in the clouds of Venus, or in the ancient rocks of Mars, it would actually be terrible news. Because it would mean that life arises commonly, which would imply that the Great Filter is not the origin of life, but something that comes later. And if it comes later, it might come for us. The third solution is the zoo hypothesis. Perhaps intelligent civilizations exist in the cosmos, but are deliberately not making themselves known to us, for reasons analogous to why we don't interfere with uncontacted tribes in remote regions of the Amazon. The galaxy might be full of civilizations that are watching us develop, waiting for some threshold of maturity before making contact. The fourth solution involves the sheer vastness of space and time. Perhaps the signals are there, but we aren't looking in the right ways. We've been listening with radio telescopes for about 60 years. Advanced civilizations might be communicating with neutrinos, or gravitational waves, or methods we haven't even conceived of. Our SETI efforts, while heroic, cover a tiny fraction of the frequencies, directions, and signal types that might carry alien communications. The fifth solution involves the lifetime of civilizations. Perhaps intelligent civilizations are common but short-lived. They arise, produce radio waves and other detectable signals for a few centuries, and then either go extinct or transition to forms of technology that are invisible to us. The window during which a civilization emits detectable signals might be so brief, compared to the age of the galaxy, that the chances of two civilizations overlapping in time are minute. And then there is the dark forest solution, made famous by the Chinese science fiction author Liu Cixin, but also a serious hypothesis in the SETI community. The idea is that the universe is a dark forest in which every civilization is a silent hunter. Silence is safety, because announcing your presence to the cosmos invites destruction for more advanced civilizations that know resources are finite and threats must be eliminated preemptively. In this scenario, the silence of the cosmos is not the absence of intelligence, but the sound of everyone hiding. Each of these solutions has implications that range from mildly unsettling to deeply frightening. And none of them has been ruled out. We don't know the answer to the Fermi paradox. We don't know if we're alone, or one of many, or one of the last survivors of a cosmic catastrophe we haven't yet noticed coming. What we do know is that the search for life in the universe is more scientifically serious now than it has ever been. The discovery, in recent decades, of thousands of exoplanets, planets orbiting other stars, has fundamentally changed our perspective. We now know that planets are common. Almost every star has planets, and many of those planets are in the habitable zones of their stars. The James Webb Space Telescope is now capable of analyzing the atmospheric composition of exoplanets by studying the light that passes through their atmospheres as they transit their stars, a technique called transmission spectroscopy, detecting biosignatures, oxygen, methane, ozone in combinations that strongly suggest biological activity in an exoplanet's atmosphere would be one of the most transformative discoveries in human history. We have not yet found one, but we're looking. And closer to home, the discovery of extremophiles, organisms that thrive in conditions once thought incompatible with life, has expanded our conception of where life might exist. Organisms have been found living in deep-sea hydrothermal vents, in highly acidic hot springs, in the sub-zero brines of Antarctica, in highly radioactive environments, in the stratosphere. Life, on Earth at least, is astonishingly persistent and adaptable. The subsurface oceans of Jupiter's moon Europa and Saturn's moon Enceladus are particularly exciting targets. Enceladus has been shown by the Cassini spacecraft to be actively venting water vapor and organic molecules from its subsurface ocean through cracks in its icy surface. A subsurface ocean that contains liquid water, organic chemistry, and hydrothermal activity. All three ingredients are present. Whether life has arisen there, we don't know. But it's not an unreasonable place to look. And Mars. We know that ancient Mars was warmer and wetter than it is today. Ancient river channels, lake beds, and mineral deposits left by liquid water testify to a Mars billions of years ago that might have been habitable. Life, if it arose on early Mars, might have retreated underground as the planet lost its atmosphere and surface water, and could potentially still exist in subsurface environments today. Finding life on Mars, or finding fossil evidence of ancient Mars life, would be extraordinary. It would either confirm that life arises independently on multiple worlds, or it would raise the fascinating possibility that life on Earth and Mars share a common origin, seeded by meteorites, in a process called lithopanspermia. And now, let me introduce you to something that has recently moved from the fringe to the center of serious scientific discussion. Something that has captivated public attention and generated genuine scientific interest for the first time in decades. Unidentified aerial phenomena, UAP. For the better part of the 20th century, UFOs were associated with fringe culture, conspiracy theories, alien abductions, tabloid headlines. Serious scientists and government officials avoided the topic for fear of being associated with the fringe. And because so much of what was claimed in the UFO community was clearly exaggerated, misidentified, or outright fabricated, the entire subject was tainted by association. But something changed. In December 2017, the New York Times published an investigative piece revealing the existence of a classified Pentagon program called the Advanced Aerospace Threat Identification Program, or ADIP, which had been secretly studying reports of unidentified aerial phenomena encountered by military personnel. Along with the article came extraordinary footage. Gun camera videos from Navy aircraft showing objects moving in ways that appeared to challenge known aerodynamic principles. No visible propulsion, no aerodynamic surfaces, sudden accelerations, ability to transition between air and water, and in one case, a shape that prompted the Navy pilots to call it a tic-tac. The revelation was significant not because it proved alien spacecraft. It didn't, not by any stretch, but because it demonstrated that genuine, credible reports of unexplained aerial phenomena were being taken seriously by military and intelligence institutions. The pilots who had encountered these objects were trained observers flying advanced aircraft with sophisticated sensors. Their testimony was credible, and the footage was real. In 2020 and 2021, the Navy officially released 3 videos: the Gimbal, FLIR 1, and Go Fast videos, and acknowledged they had not been able to identify what was in them. In 2021, the Office of the Director of National Intelligence released a preliminary assessment of UAP, acknowledging 144 reports from military personnel between 2004 and 2021, of which only one could be confidently identified as a conventional object. The rest remained unexplained. In 2023, a former intelligence official named David Grush testified before Congress under oath that the U.S. government had in its possession retrieved materials and intact craft of non-human origin, and that there was a secret program to recover and reverse engineer these materials. This testimony was extraordinary and received significant media coverage. It has not been independently verified, and the government denied the claims. But the fact that a credible former senior intelligence official was willing to make such claims under oath, with the legal protections of a federal whistleblower, was remarkable. What should we make of all this? The scientific community remains largely skeptical that any of the UAP evidence points to alien spacecraft. Most UAP reports are almost certainly mundane objects: drones, weather balloons, atmospheric phenomena, sensor glitches, adversarial nation-state technology, misidentified by observers in confusing and stressful conditions. This is the likeliest explanation for the great majority of cases. But most is not all. And the scientific approach is not to dismiss the unexplained, but to study it. In 2022, NASA announced that it was forming its own independent team to study UAP, and in 2023 released a report that called for better data collection, more rigorous analysis, and a scientific approach to the phenomenon. The report noted that the stigma associated with UAP reporting had discouraged trained observers from making reports, which meant the data quality was poor, and recommended steps to improve it. The honest position is this: most UAP are almost certainly explainable by conventional means. But we don't know that with certainty for all of them. And the scientific method demands that we investigate, not dismiss. If even a handful of UAP represents something genuinely unprecedented, a new physical phenomenon, advanced technology from a terrestrial adversary we don't know about, or, in the most extraordinary case, something else entirely, then understanding the matters enormously. I am not suggesting that alien spacecraft are visiting Earth. I am suggesting that unexplained things deserve scientific investigation, and that for too long, stigma prevented that from happening. Now, it finally seems like it might. Now let's turn from the speculative fringes back to the rock-solid center of observational astronomy, because there is one more phenomenon that I want to walk you through. Something that has been observed beyond any doubt, something that no conventional physics can explain without invoking physics we don't understand. Something that is, in a very literal sense, the universe speaking to us in a language we can't quite translate. I want to talk about the Hubble tension. The universe is expanding. We've established that, and we can measure the rate of that expansion, called the Hubble constant, or h, in multiple ways. The first way is to look at the local universe. Measure distances to nearby galaxies using standard candles like Cepheid variable stars and Type Ia supernovae, and use those distances combined with the recession velocities of galaxies to infer age. This has been done with extraordinary care by teams like the Hubble Space Telescope Key Project and the SH0ES team, led by Adam Rees, the same Rees who helped discover dark energy. Their current best measurement gives a Hubble constant of approximately 73 kilometers per second per megaparsec. That means for every megaparsec, roughly 3.3 million light-years of distance between two objects, those objects are receding from each other at 73 kilometers per second due to the expansion of the universe. The second way is to look at the early universe, analyze the cosmic microwave background radiation, and fit it with the lambda CDM model to infer H from the CMB data. This has been done with extraordinary precision by the Planck satellite team. Their result, approximately 67 to 68 kilometers per second per megaparsec. These two numbers are different, not slightly different. They are in tension by approximately 5 standard deviations, which in physics is generally considered the threshold for claiming a discovery. Each team has gone over their methods exhaustively. Systematic errors have been meticulously ruled out. Multiple independent groups have confirmed both results using different methods. The tension appears to be real, and it is deeply troubling because the lambda CDM model, which fits the CMB data so beautifully and gives H of 67, should also describe the local universe from which the H of 73 is derived. There is no room in the model for them to be different, but they are. And as measurement precision has improved over the past decade, the tension has gotten worse, not better. The discrepancy has not gone away with more careful measurement. It has persisted and sharpened. This could be, some theorists hope, a hint of new physics. Early dark energy, a form of dark energy that was active in the early universe and has since faded, is one popular proposal that could relax the tension. Modified theories of gravity have been proposed. Interactions between dark matter and dark energy. New light species of particles. Additional types of neutrinos. No single proposal has one broad acceptance, and none fits all the data perfectly. It could also be, some cautious observers suspect, a subtle yet unidentified systematic error in one or both measurements. Measuring cosmological distances is fiendishly difficult, and the error bars, while impressively small, might be underestimated. But the fact that two completely independent methods of measuring the same physical quantity, using completely different physics at completely different cosmic epochs, give results that disagree at 5 sigma is not something you can just wave away. If it's real, if it's not a systematic error, it means there is something wrong with our model of the universe. Something is missing, and whatever it is, it has been affecting the expansion history of the universe in a way our best model doesn't capture. The Hubble tension might be the crack in the dam, the small inconsistency that, when finally understood, breaks open a completely new understanding of how the universe works. Or it might be a systematic error that gets resolved with better data. We don't know yet, but we're close. New observations from the James Webb Space Telescope, new data from large galaxy surveys like the Vera Rubin Observatory's upcoming Legacy Survey of Space and Time, which will image billions of galaxies and produce an unprecedented map of the cosmos, and new constraints from gravitational wave measurements will all bring additional precision to this measurement over the next decade. If the tension persists, it becomes a crisis. And crises in physics are how revolutions happen. Let me now circle back to something we touched on earlier, the cosmic microwave background, and explore an even stranger possibility that has emerged from careful analysis of its patterns. Because some researchers claim to have found something in the CMB that shouldn't be there. Something so strange it has been given a name that suggests its nature: anomalies. Beyond the cold spot, the CMB shows other features that don't quite fit the lambda CDM model. There is what's called the hemispherical asymmetry, the fact that the CMB fluctuations on one side of the sky are statistically slightly stronger than on the other side. There is the alignment of the largest scale modes, called the quadrupole and octopole, which are strangely aligned with each other and with the plane of the ecliptic, the plane of the solar system. These alignments are so unlikely by chance that they've been nicknamed the axis of evil by some cosmologists. Now, these anomalies might simply be statistical flukes, unlikely but not impossible features in a finite realization of a random process. When you flip a coin 10,000 times and look for patterns, you will always find some. But the CMB anomalies are persistent, and they have been confirmed in multiple data sets from different satellites. The Planck satellite team, after exhaustive analysis, classified them as anomalies that are present in the data but whose statistical significance is insufficient to claim they represent genuine departures from the lambda-CDM model. But some theorists have been much more excited. They have proposed that the CMB anomalies might be signatures of physics from before the Big Bang, a concept that sounds contradictory but arises naturally in certain theoretical frameworks. In the cyclic cosmology model of Paul Steinhardt and Neil Turok, for example, our Big Bang was not the beginning of everything, but a collision or bounce in a higher dimensional framework called the ekpyrotic universe, and evidence of previous cycles might be imprinted in the CMB. In Roger Penrose's conformal cyclic cosmology, our universe is just the latest in a series of eons, each ending in an expanding, cooling universe that reinitiates a new Big Bang. And Penrose has claimed to see concentric ring patterns in the CMB that he interprets as echoes of collisions of supermassive black holes in a previous aeon. Most cosmologists are skeptical of these specific claims. The statistical significance of Penrose's rings has been disputed, and the cyclic models face their own theoretical challenges. But the fact that serious physicists are proposing that we might see evidence of physics from before the Big Bang, imprinted in the oldest light we can observe, illustrates just how far we're willing to push the boundaries of imagination in search of explanation. Let me now take you somewhere truly extreme, to the very edge of what we know, the observational horizon beyond which we cannot see. But before we get there, let's talk about something in between, something in the middle distance of cosmic scales, something that is real and observed and deeply mysterious.
Filaments, sheets, voids, the cosmic web.
When you zoom out far enough, past individual galaxies, past galaxy clusters, past the scales of tens of millions of light years, the universe reveals a structure that is breathtaking in its complexity and its beauty. Galaxies are not distributed randomly throughout space. They are concentrated along enormous filaments, threads of matter hundreds of millions of light years long, that intersect at nodes called galaxy clusters. Between the filaments are vast, near-empty voids, cosmic bubbles of space where almost nothing exists, spanning hundreds of millions of light years. This three-dimensional tapestry, the cosmic web, looks remarkably like a neural network, like the mycelium of an enormous cosmic fungus, like a brain. The resemblance is striking enough that researchers have actually compared the structural properties of the cosmic web to the structure of neural tissue and found surprising statistical similarities, though the physics involved are completely different, and the resemblance is almost certainly a coincidence arising from similar mathematical processes, not any deep connection. The cosmic web was predicted by computer simulations of structure formation, starting from the tiny fluctuations in the CMB and running the gravitational dynamics of dark matter and ordinary matter forward in time for billions of years. And the predictions match the observations beautifully. The largest galaxy surveys, including the Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, and the ongoing DESI Survey, have mapped the three-dimensional distribution of millions of galaxies and confirmed the cosmic web structure in extraordinary detail. But embedded in this structure are mysteries. The voids, for instance, are almost empty, but not completely. There are galaxy surveys that suggest the voids contain tendrils of galaxies, faint filaments weaving through the emptiness. There is evidence that the properties of galaxies in the walls and filaments of the cosmic web differ from the properties of galaxies in dense cluster environments, suggesting that large-scale structure influences the evolution of individual galaxies in ways we're still working out. And the largest voids are genuinely vast. The Boötes void, discovered in 1981, is approximately 330 million light-years across and is so empty that the few galaxies it contains are arranged in a shell around the interior, as if something swept out the middle. Its existence, while not in stark conflict with cosmological models, is unusual enough that it has attracted speculation, though most of that speculation is unwarranted. And then there is the Hercules Corona Borealis Great Wall, a structure discovered in 2013 and updated in subsequent analyses, a vast concentration of galaxies spanning roughly 10 billion light-years. If confirmed, it would be the largest known structure in the observable universe. But there's a problem, according to the Lambda CDM model and the cosmological principle, which states that the universe is homogeneous and isotropic when viewed at large enough scales. Structures larger than a few hundred million light-years shouldn't exist. Structures this large would require more time to form than the age of the universe, given the gravitational dynamics of our models. The Hercules Corona Borealis Great Wall is controversial. Some researchers dispute its reality, arguing that it is an artifact of how the data was analyzed. But if it is real, it is one of the most significant challenges to the cosmological principle and the standard model of structure formation. The cosmological principle is not just a convenience. It's built into the foundations of our cosmological model. If it turns out to be wrong on large scales, the entire framework of modern cosmology needs revision. And there are other hints. A 2020 analysis of hundreds of thousands of galaxies found that the universe might not be as uniform as expected at scales of several hundred megaparsecs. A 2023 study found that the direction in which the universe appears to expand fastest seems to depend slightly on which direction you look, a suggestion of subtle large-scale anisotropy. These results are preliminary and disputed, but they are being taken seriously. If the cosmological principle is wrong, if the universe has structure on scales larger than our models predict, then we might need to rebuild our understanding of cosmology from the ground up. The implications would be profound, touching everything from our estimates of the Hubble constant to our models of the Big Bang itself. And now let's address something that may be the most profound and mind-bending idea in contemporary physics. An idea that is no longer confined to the pages of theoretical journals, but is increasingly becoming the subject of serious experimental effort. Simulated reality. In 2003, philosopher Nick Bostrom at Oxford University published a paper making a simple but devastating argument. He pointed out that if it is possible to create computer simulations realistic enough that simulated beings within them would think they were real, and given the trajectory of computing technology, this seems plausible, then advanced civilizations could, in principle, run enormous numbers of such simulations. If they do, then the number of simulated minds in all the simulations combined would far, far outnumber the real minds in the original base reality. And if that's the case, then any randomly chosen mind, including yours, is almost certainly a simulated mind in a simulated universe, not a real mind in base reality. This is the simulation argument, and it has been taken seriously by a surprising number of scientists and intellectuals. Elon Musk has called it likely that we're in a simulation. Physicist Sabine Hossenfelder has argued against it. Astrophysicist Neil deGrasse Tyson gave it 50-50 odds at a 2016 symposium. The argument is logically tight, and the only ways to escape its conclusion involve denying the premises. Either it's impossible to create realistic simulations, or no civilization ever bothers to create them, or consciousness in simulated beings can't arise. From the scientific standpoint, the question is whether we can find any observable evidence that would distinguish a simulated universe from a real one. Some researchers have proposed that certain features of physics might be telltale signs of an underlying computational structure, discrete spacetime, for example, or the existence of fundamental constants that look like parameters that were set by a programmer. Others have argued that the fact that the laws of physics are mathematical and computable is suspicious, as if reality were designed to be simulatable. But these arguments are very weak as evidence. The discreteness of quantum mechanics and the mathematical nature of physical laws can have explanations that don't involve simulation. There is no compelling observational evidence that we live in a simulation, but there is also, arguably, no observation that could definitively rule it out, which is what makes it simultaneously fascinating and infuriating from a scientific perspective. It may not be a scientific question at all, in the strict sense of a question that can be tested by experiment. And yet it persists. Because the question of whether our reality is ultimate or derivative, whether the universe we inhabit is the deepest level of existence or just one layer in a hierarchy, is one of the most ancient questions of philosophy, wearing new mathematical clothing. Let's now come back to something intimately connected to all of this, the question of consciousness. Because if there is one phenomenon in the observable universe that is truly inexplicable, it might not be dark matter or dark energy or quantum mechanics. It might be the thing that is observing all of these phenomena. It might be the subjective experience of being alive, of being aware, of being you. How does consciousness arise from matter? This is called the hard problem of consciousness, coined by philosopher David Chalmers in 1995, and it remains completely unsolved. We understand a great deal about the neural correlates of consciousness, the brain activity that correlates with particular conscious experiences. We can trace the information processing, the neurotransmitter activity, the electrical patterns that correspond to perception, emotion, and thought. But none of this explains why these processes are accompanied by subjective experience, why they feel like something, why there is something it is like to be you. This is not a problem that neuroscience alone can solve, because the problem is not just about mechanisms, it's about the nature of experience itself. Why does the physical process of photons striking the retina, being converted to electrical signals, and being processed by the visual cortex produce the experience of the color red? Why does it feel like anything at all? The question matters for our understanding of the universe, because if consciousness is something genuinely new that emerges from the complexity of certain physical systems, a property that the laws of physics as currently written don't include, then our picture of reality is fundamentally incomplete. The universe has been evolving for nearly 14 billion years, and at some point in that evolution, it became aware of itself. That is an extraordinary fact, and it demands explanation. There are many philosophical positions on consciousness. Dualism, which holds that mind and matter are fundamentally different substances. Physicalism, which holds that consciousness is entirely a product of physical processes. Panpsychism, which holds that consciousness or proto-consciousness is a fundamental feature of all matter, and that human consciousness is what you get when enough of this fundamental consciousness is organized in the right way. And illusionism, which holds that the apparently inexplicable quality of conscious experience is itself an illusion, a cognitive mistake that dissolves on careful analysis. Each of these positions has articulate defenders and devastating critics, and none has been conclusively established. Some physicists, most controversially Roger Penrose and anesthesiologist Stuart Hameroff, have proposed that consciousness involves quantum processes and structures inside neurons called microtubules, and that quantum effects at this level might account for features of consciousness that classical computation cannot. This is called the orchestrated objective reduction, or orchestroir hypothesis, and it remains highly controversial. Most neuroscientists and physicists consider it unsubstantiated. Others, like physicist Max Tegmark, have proposed that consciousness is a state of matter, a particular kind of information processing that arises whenever a physical system satisfies certain mathematical criteria related to integrated information theory, a framework developed by neuroscientist Giulio Tononi. What is most striking is that despite centuries of philosophical inquiry and decades of neuroscientific research, we have not moved significantly closer to answering the hard problem of consciousness. We have explained many of the functional and mechanistic aspects of cognition, but the essence of experience, what it means to be aware, remains as mysterious as ever. And in the context of our exploration of the universe's unexplained phenomena, this is significant. Because if consciousness is unexplained, if we don't understand how the matter of the universe became self-aware, then we are missing something fundamental. Not just about the brain, but about the nature of matter and reality itself. The universe produced you. It produced this moment of awareness, this experience of listening, this feeling of wonder at the vastness of what you don't know. How? Why? These may be the deepest questions of all. Now let me tell you about something that occurred in the universe so long ago, so far away, and so violently that it staggers the imagination. And yet it left a fingerprint that we can see today, a fingerprint woven into the very fabric of space. I want to talk about cosmic inflation. The Big Bang model has extraordinary successes. It predicted the cosmic microwave background. It explains the abundances of hydrogen, helium, and lithium formed in the first minutes. It explains the expansion of the universe. But it has some serious problems of its own, problems that led physicists to propose a radical modification in the 1980s. The first problem is the horizon problem. The cosmic microwave background is extraordinarily uniform. Its temperature is the same to 1 part in 100,000 in every direction we look. But regions of the CMB that appear in opposite directions of the sky were so far apart at the time the CMB was emitted that they could never have been in causal contact. Light from one side could not have reached the other in the time available before the CMB was emitted. They should never have had time to reach the same temperature, and yet they did. How? The second problem is the flatness problem. The universe, on the largest scales we can observe, appears to be spatially flat. Its geometry is Euclidean, with parallel lines staying parallel. General relativity allows for 3 possible geometries: positively curved, like a sphere, negatively curved, like a saddle, or flat. The flat solution is unstable. Tiny deviations from flatness in the early universe would grow over time, producing a strongly curved universe today. For the universe to be as flat as we observe, its geometry in the very early universe must have been tuned to flatness with extraordinary precision. 1 part in 10 to the 60th. Again, why? The third problem is the absence of certain relics. Grand unified theories predict that in the extreme conditions of the early universe, exotic particles called magnetic monopoles should have been produced in abundance. But we have never detected a single magnetic monopole. Where did they go? In 1980, physicist Alan Guth proposed a solution to all 3 problems at once: cosmic inflation. The idea is that in the very first moments after the Big Bang, between approximately 10 to the negative 36 and 10 to the negative 32 seconds after the beginning, the universe underwent a period of extraordinarily rapid exponential expansion, doubling in size many times over in a tiny fraction of a second. During this inflationary period, the universe grew from something fantastically smaller than a proton to a region larger than a grapefruit in less than a trillionth of a trillionth of a trillionth of a second. This inflation would solve the horizon problem because the regions of the universe that we see as being causally disconnected were actually in causal contact before inflation began. They had time to equilibrate to the same temperature, and then inflation stretched them apart beyond the horizon. It would solve the flatness problem because any curvature of space, no matter how large, would be ironed out by the enormous stretching. The universe becomes flat for the same reason that the surface of a balloon looks flat if you blow it up enough. And it would solve the monopole problem because the density of monopoles is diluted by the enormous expansion to the point where the probability of finding one in our observable universe is negligible. But inflation predicts something else, something that ties it directly to observations. The quantum fluctuations in the inflationary field, the tiny random variations in the density of the inflating vacuum, would be stretched by inflation from quantum scales to cosmic scales, becoming the seeds of the density fluctuations we observe in the CMB. And the predicted spectrum of those fluctuations, how their amplitude varies with scale, is a very specific mathematical form called a nearly scale-invariant Harrison-Zeldovich spectrum. This prediction was tested against CMB observations and found to be correct with extraordinary precision. This is a genuine predictive success. But inflation has problems of its own. The first is that inflation is not a specific model but a framework. There are dozens of specific inflationary models, each making slightly different predictions, and it's not clear which, if any, is correct. The second is that inflation, once it begins, tends to be self-reproducing. Different regions of the inflating space inflate by different amounts and produce bubbles with different properties, leading naturally to an eternal inflationary multiverse. This is the same multiverse we've mentioned before, and it carries the same virtues and problems. It explains fine-tuning but resists testing. The third problem is one of the most exciting frontiers in observational cosmology today. Inflation predicts that, in addition to density fluctuations, it should have produced gravitational waves, ripples in the fabric of space-time from the inflationary period itself. These primordial gravitational waves would leave a distinctive imprint in the polarization of the CMB, a pattern called B-mode polarization. If detected, B-mode polarization from inflation would be the most direct evidence for the inflationary paradigm and would allow us to constrain which model of inflation is correct. In 2014, the BICEP-2 team announced what they thought was a detection of inflationary B-modes, a result that sent shockwaves through the physics community, with a level of excitement rarely seen in science. But subsequent analysis showed that the signal they had detected was actually contamination by polarized dust in our own galaxy, not primordial inflation. It was a false alarm, and a painful lesson in the difficulty of these measurements. The search for primordial B-modes continues. The BICEP/Keck collaboration, the South Pole Telescope, the Simons Observatory, and ultimately the proposed CMB-S4 experiment are all working to push sensitivity to the level where inflationary B-modes, if they exist, can be detected. If they find them, it would be one of the greatest scientific discoveries of the 21st century. If they don't find them, if the sensitivity exceeds what inflation predicts, it would rule out a broad class of inflationary models and potentially force a rethinking of the very earliest moments of cosmic history.
We are waiting, watching, listening for a whisper from the very beginning of time.
And now, as we approach the end of this journey through the most unexplained phenomena of the observable universe, I want to step back and look at all of this together, to feel the full weight of what it means to be a conscious creature in a universe that is 95% invisible, that is accelerating apart under the pressure of a force we don't understand, that began from conditions we can't explain, that evolved toward complexity we can't account for, and that produced beings capable of asking why. The relationship between all of these mysteries is not coincidental. Dark matter, dark energy, the fine-tuning of constants, the matter-antimatter asymmetry, inflation, the quantum gravity incompatibility. They are all facets of the same fundamental incompleteness of our knowledge. We have a model, a spectacularly successful model, of a universe that is 27% dark matter, 68% dark energy, and 5% ordinary matter, expanding from a hot, dense beginning 13.8 billion years ago, structured by gravity and dark matter into galaxies and cosmic web filaments, and cooling toward an eventual thermal death in the far future. This model fits almost everything we observe. But the foundations of the model are built on sand. We don't know what 68% of the universe is. We don't know what 27% of the universe is. We don't know what happened in the first moments. We don't know how matter survived antimatter. We don't know how to reconcile our two most successful theories of physics. In other words, we understand 5% of the universe, and even within that 5%, there are profound mysteries about consciousness, the arrow of time, and the nature of quantum reality. Now ask yourself this, and really sit with it. In a universe where we understand so little, what extraordinary discoveries might lie just beyond the current horizon of our knowledge? What would it mean for our civilization if we solved just one of these mysteries? If we identified dark matter, or understood dark energy, or found the path to quantum gravity? History shows that great scientific revolutions don't just change our understanding of isolated phenomena, they change everything. Newtonian mechanics led to the Industrial Revolution. Maxwell's electromagnetism led to radio, television, and global communication. Quantum mechanics led to semiconductors, lasers, and the digital age. Relativity led to GPS navigation and nuclear energy. What technology, what unimaginable capability might emerge from a true understanding of dark matter, of quantum gravity? What would it mean to understand the nature of space-time at its most fundamental level? Could we someday manipulate it? Could we someday use the energy of the vacuum, dark energy, in ways we can't currently conceive? Could we someday visit the stars or communicate across the galaxy in ways that become possible only with physics we haven't discovered yet? These are speculative questions. We don't know the answers. But the history of science is the history of taking what seemed impossible and making it ordinary. 200 years ago, the idea of instantly communicating with someone on the other side of the planet would have seemed like magic. 100 years ago, the idea of splitting the atom would have seemed like alchemy. 50 years ago, the idea of sequencing the human genome seemed impossibly ambitious. The universe has always been stranger and richer than our models of it. Every time we've pushed the boundary, Every time we've looked deeper, measured more precisely, thought more carefully, we've found that reality goes further than we imagined. The fact that we don't understand most of what exists is not a sign of failure. It is a sign of how young we are, how new our tools are, how recent our science is, compared to the age of the universe. We've had radio telescopes for less than a century. We've had gravitational wave detectors for less than a decade. We've been doing modern cosmology for barely 100 years, in a universe that is 14 billion years old. We are infants. Brilliant, curious, extraordinary infants. And the universe is vast, patient, and full of secrets. There is something that physicists rarely say publicly, but that many feel privately, a kind of religious awe when they contemplate the depth of their own ignorance. Not despair, but wonder. Because every unanswered question is also an invitation. Every mystery is a door. And unlike the mysteries of human history, which are ultimately about the behavior of a single species on a single planet, the mysteries of the observable universe are mysteries of existence itself. Of why there is something rather than nothing. Of what space and time really are. Of why the laws of nature are what they are. Of whether there is life on other worlds, other civilizations, other minds contemplating the same darkness. Richard Feynman, one of the greatest physicists of the 20th century, once said that it is perfectly consistent to live and not know. You do not need to know where matter comes from to enjoy it. You do not need to understand dark energy to feel its effects. You do not need to solve the hard problem of consciousness to have a rich and vivid experience of being alive. But knowing the questions, holding the deep mysteries in your awareness, feeling their weight, appreciating how extraordinary it is that we have progressed far enough to even frame them, this enriches everything. The stars are more beautiful when you know they are forged hydrogen, helium, and heavier elements synthesized in nuclear furnaces. The night sky is more magnificent when you know that each point of light is a sun, surrounded by worlds, receding from you in an expanding cosmos. The ground beneath your feet is more astonishing when you know it is 5% of a universe 95% invisible, a thin crust of ordinary matter resting on a dark sea. And the questions, the great, unanswered, humbling questions, are perhaps the most beautiful things we have produced as a species, because they are the evidence of our most distinctly human quality, the desire to understand, not just to survive but to know, not just to live but to wonder.